Good day to you all. Today we will be learning how to name ethers. In this tutorial, I will teach you the rules for naming, the formula, and many examples to supplement the lesson. So according to William Rouge, I don't know if I'm pronouncing it correctly, ethers are compounds having two alkyl or aryl groups bonded to an oxygen atom. It has the formula R prime connected to this oxygen atom connected to this R prime. And its substituent prefix is alkoxy. So there are two ways of naming ethers, the simple and intermediate ways. For simple ether naming, when a simple alkyl or aryl group is bonded to an oxygen atom, the names of the alkyl or aryl groups are written in alphabetical order, then the word ether is added in the end. Now let's have some examples. We have this ether right here, and it's named diethyl ether. Why is it named diethyl ether? Now, if we go back to in the instructions on how to name this, the alkyl or aryl groups connected to the oxygen atom will be written in alphabetical order. Now, this group here and this group here are both ethyl. They're both the same thing. And if you were to name this would have been ethyl, ethyl, ether. But to simplify, we can just put the word di, which means two or double. So it would just be named diethyl ether. So now let's move on to the intermediate ethers. So in naming intermediate ethers, if one of the groups is more complex, then the ether group is treated as an alkoxy substituent. So basically, the more complex group defines the root. We have this example right here. This is 1-methoxypropane. As you can see, it doesn't have that ether behind it anymore. So now why is this named 1-methoxypropane? So we said a while ago that the complex group defines the root. Basically, what this is saying that this propane group here, right here, is the main group, and this ether group is just connected to it. We will treat this as the main group that will drive the name. So this is a propane, its root will be propane. Now why 1-methoxy? Now if you put names into substituents, you will have the number will be the lowest number that it can be named after. So for example, we have this methoxy group here, methyl, and then oxygen. And remember that the substituent is alkoxy, the alkyl group here is methyl, so methoxy, that's where it came from. It's connected to the first carbon atom. If this was placed over here, this time, this would be the first, and this would be 2 still, and this would be 3. So now since this is connected to the first carbon atom, well, this would be named 1-methoxy, because connected to 1, then methoxy, then propane to signify the group. That would define the whole name. Now let's go to more examples so that we can analyze how this is named better. We have this right here. This is 2-methoxy, 2-methylpropane. Now, remember that this is the main group right here. This is the propane. 1, 2, 3. Or 1, 2, 3. But we'll use this propane group to make it clear. So now, this is a propane, so propane will be the root here. And why is this 2-methyl? In the past rules, when we name the substituents for alkenes and alkynes, it goes the same way. The methyl group, this methyl group right here, is connected to the second carbon atom of this propane. So it's 2-methyl. Now this other group, this methoxy, is also connected to the second atom. That's why it is 2-methoxy-methylpropane. For reaction of ethers are relatively inert towards the reaction, and they usually show good solvent properties for many non-polar organic compounds. This strong dissolving power, coupled with low reactivity, makes ethers good solvents in which to run reactions. So an acid-catalyzed cleavage that occurs when hydroiodic acid mixes with ethers is the most significant reaction that ethers experience. The mechanism for this reaction is like this.
There are multiple uses for ethers. One is in fuel. Dimethyl ether is a well-known ether. Since dimethyl ether is a hydrocarbon with 2 methyl groups bonded to an oxygen, it has an extremely low boiling point of negative 23.6 Celsius. One other ether that has another use is diethyl ether. In many laboratories, diethyl ether is used as a solvent, and because diethyl ether is nonpolar, it dissolves other nonpolar substances and is not miscible with polar substances like water.
Let's talk about alcohols. Now, to describe an alcohol simply using a drawing, it's just this. As you can see, there's an OH connected to this carbon group right here. Now let's try to name this. So we find the longest carbon group, 1, 2, 3, 4, 5. That's a pentane. Then we see where this is connected. This is connected to the second carbon group, as we can see here. So this would be pentan dash 2 all. Now as you can see, there's all here. That's its substituent prefix right there, all. So now let's move on to the types of alcohols. There are 3 types of alcohols. There's a primary, secondary, oh my gosh, sorry for the mistake, and tertiary. Now, for the primary alcohol, In primary alcohol, the carbon which carries the OH group is attached to one alkyl group. Now here are some examples of primary alcohols. We have this. This OH is connected to one carbon atom, and this carbon atom is connected to another one carbon atom. This is called ethanol. You'll start to see the pattern. Why? Ethane, and now it's connected to the first carbon atom because we counted from here. So ethanol. Another example, we have, now we'll look for the longest carbon chain here, which is 1, 2, 3. That's the longest carbon chain. Why did I start here? We usually start first with where the functional group is. So 1, 2, 3. 1 is where this OH group is, and apparently at 2 we have a methyl group. Unless you count from here, 1, 2, 3, then this is the methyl group. But it doesn't matter. So how do we name this? This would be 2-methyl. Why is it 2-methyl? Because it's the second carbon. 1, 2. 2-methyl propan 1-ol. 2-methyl propan 1-ol. Now let's start with secondary alcohols. So in a secondary alcohol, the carbon with the OH group attached is joined directly to two alkyl groups, which may be the same or different. Now here's an example. You'll definitely see a difference from the primary alcohols here. This is a secondary alcohol right there. Now, compared to the primary alcohols, the carbon atom which the OH is connected to is only connected to one other carbon atom. Look at that. This carbon atom is connected to two other carbon atoms. That's why it's called secondary. Now, let's name this. So, we'll look for the longest carbon chain. 1, 2, 3. It's a propane. Now, where is this OH group connected to? To the second carbon atom. So, this would be propan 2-ol. Now, let's move to the next one. This is another secondary atom. I'm sure you've already seen the differences. This carbon here is connected to only one. In this one, because carbon here is connected to two. The same thing. Now let's try and name this. This would be named pentan 3-ol. Why is this named pentan 3-ol? Well, we have identified the longest carbon chain as a 5 carbon group. 1, 2, 3, 4, 5. And then it's at the third atom where this OH group is connected to. Now, let's go to tertiary alcohols. In tertiary alcohols, the carbon atom holding the OH group is attached to directly 3 alkyl groups instead, which may be a combination of the same or different. So, it's just like this, but imagine having another one here. Let me give an example. That is a tertiary alcohol. This is named 2-methyl propan 2. Oh, the name's pretty long. Well, I'll explain why. So, we've identified the longest carbon chain to be a propane. Why? 1, 2, 3. Or 1, 2, 3. And then, connected to this carbon chain are there two groups. This OH group, which is our main group that we're studying right now, and this methyl group right here. So, this methyl group is connected to the second carbon atom. This OH group is also connected to the second carbon atom. But since we usually name this OH group at the end here, at the root, we'll just name the 2-methyl here in front. So, since it's the second carbon atom, it would be 2-methyl propan, then 2-ol. Reactions of alcohols. So, because alcohols are easily synthesized and easily transformed into other compounds, they serve as important intermediates in organic synthesis. So, one reaction of alcohols is oxidation, where alcohols may be oxidized to give ketones, aldehydes, and carboxylic acids. Another is dehydration to alkenes. Converting an alcohol to an alkene requires removal of the hydroxyl group and the hydrogen atom on the neighboring carbon atom. Another is dehydration to esters, where under carefully controlled conditions, simple alcohols can undergo intermolecular dehydration to give ethers. Esterification. Alcohols can combine with many kinds of acids to form esters. There are multiple applications for alcohols. The most famous one is that it could be a beverage. One of the most commonly served beverages in the world, ethanol, is consumed by millions of adults each year. It could also serve as fuel. You could burn it. The first 4 alcohol functional groups can be biologically synthesized and be used as an alternative to fossil fuels as they burn very cleanly. You can also dissolve it, as ethanol is widely used as a solvent, and you can use to clean with it, as methylated spirits or isopropyl alcohol can be used to clean industrial machinery.